So let's discuss. Work is measured in joules as well as energy. A joule is a Newton meter. The idea is that we are measuring the ability to do work in the number of joules that we have. So the equation for work is force dot distance. These are all vectors except for work, which is a scalar, because work is a number. It has no direction. It is the amount of energy that was used in having that force work through that distance. Okay, so we can find work pretty easily. Make sure that if they are not pointing, if the force and distance are not pointing in the same direction, that you use the magnitude of the force times the magnitude of the distance cosine of the angle in between them. So we did a problem where you have a lawnmower and someone is pushing on that lawnmower at, let's say, a 30-degree angle, and their force is 100 newtons, and it travels this way for 10 meters. The work done would be the force, which is 100 newtons, the magnitude, so we take no direction, distance was 10 meters, and then cosine of theta, the angle in between them, cosine of 30. So that would be 100 times 10 times cosine of 30, which is 1,000 square root of 3 over 2 joules. So that would be 500 square root of 3 joules. All right, so that is work. Now, what types of energy are we familiar with? What types of energy are we familiar with? Well, we are familiar with a couple. Gravitational potential energy. So when you have something at a height, gravity is going to pull it down, and so we can store energy by putting something at a higher altitude. That's why water towers work, because you have, you have your water tower up here. It is full of water. Yep, that's right, water. And then it is at some height above the ground. So it has potential. So when the water comes down, it can go pretty far and get all the way to your home so that you can make a delicious cup of coffee with that water, because it has gravitational potential energy in the water tower. So the equation for gravitational potential energy is the mass times the force of gravity times the height. The next type of energy that we look at is kinetic energy. So kinetic is given by the following equation: 1/2 mass times velocity squared. So kinetic energy only exists when something is moving. So if something stopped, it has no kinetic energy. If something's moving, it absolutely has kinetic energy because its velocity is not zero. So suppose you are taking a truck that is moving and has a mass of 5,000 kilograms. That's a big truck. It's moving at a velocity of 10 meters per second, and it slows to a stop. You guys like my truck? I think it's a very nice truck. We can find out how much energy went into the stopping action, right? How much energy was used by the brakes to stop, because we can find the amount of kinetic energy here. It's 1/2 times m times v squared to the kinetic energy here, which is 0. So the change in energy is the amount of work that was done. Okay, very important. Change in energy is work. And so that would be whatever 5,000 times 100 divided by 2 is. So it looks like 2, 5, 0, 0, 0, 0. That is a lot of work. And I hope I got those right. Looks right. Okay, so we can find the change in kinetic energy or the change in energy, and that's how much work was done. Finally, we have elastic potential energy, and that is most commonly done by springs. So, the force of a spring is negative kx. The work done by a spring is negative, or is 1/2 kx squared. So, the elastic potential energy of a spring, so let's say it's stretched, the unstretched length we don't really care about, but we do care about is how much it is stretched. That is the x part. So elastic potential energy, or how much energy you've stored in that spring by stretching it out, is given by this equation here. So how do these relate? Well, up to this point, we've talked about conservative types of energy. So kinetic, gravitational, and elastic. These types of energy allow transfer between one another quite easily, whereas non-conservative, like thermal, so heat, drag, those are all things like air resistance. Those are all types of energy that we really can't get back. But hopefully, if you lift something to a height, you can get that energy back by bringing it down to a lower height, like the water tower example, like we said. Okay, so those would all be conservative types of energy. These are the ones that we work with in this class. So how would I do an energy problem? First of all, just like always, we draw a picture. And next, we always like to have a reference frame. No matter what, just like the other types of problems that we saw. From here, what do? Well, the most important thing to do is to identify types of energy involved. So suppose I have a ball that is being dropped from a height of 2 meters. Okay, it has a mass 1 kilogram. What type of energy does it have at, well, we drew our picture, let's draw our reference frame. So I'm going to call y up and I'm going to call 0 at the ground. We need to identify what types of energy it has and what type of energy is involved. So of our conservative energies, because at this point in this class, we don't have the depth of knowledge to address the non-conservative types of energy. So at this point, we're looking for gravitational potential energy, kinetic energy, or elastic potential energy. Since there's no springs, there's no elastic potential energy. But I will have gravitational potential and kinetic energy involved. If it's dropped from rest, I know that it's not moving, so kinetic energy is 0 from up there. But at this point, it has plenty of gravitational potential energy because that equals mgh. So that equals 9.81 times the height. So that looks like 18 point, oh dear, did I forget how to do math? I might have. Oh dear. All right, 9.81 times 2 is going to be 19 point. Wow, I'm spacing on how to do math. This is really sad. I'm sorry, guys. All right, using a calculator because my brain is not working. 9.81 times 2 is 19.62. All right, cool. So that's how much energy it has initially. To find total energy, this is a little aside, total energy is just the sum of all energies that you have. So for this question, it would be gravitational plus kinetic. So the total energy for anywhere in this problem is 19.62 joules. Now, you're going to solve for what they ask you for. So, for example, I could ask, what's the speed There. Well, at the bottom, I know that my gravitational potential energy will go to 0 because H will be 0, but all of that energy is going to be transferred into kinetic energy because now it's moving. So I see this gravitational potential energy completely transfer into kinetic because I'm now at no gravitational potential energy. So if I solve this, kinetic energy is 1/2 mv squared, and that equals 19.62. I know the mass is 1, and so I can find the velocity pretty easily. It's going to be 2 times 19.62, and I take the square root of that. From there, I'll find my velocity. I'm thinking it is, using my handy calculator here, 6.26 meters per second. Since I was given 2 or 3 significant digits, I'm going to continue with 3, and that's my answer. So that's how you do an energy problem. You want to draw a picture, draw your reference frame, identify the types of energy that you're going to have, and then solve for the unknowns each time. And that's it. So thanks for joining me for this lesson on energy.